This is a very easy and I would say interesting concept because you have to follow some standard rules. But yes, having said that, there are cases where the question can get complicated, but for the most part, this is fairly easy, okay? And it's like it's one of those topics where you can say for sure what the first part is going to ask, what the following part is going to ask, okay? And there's a standard rule for pretty much every single question, okay? So this is a continuation of Newton's laws of motion, okay? It's a continuation of Newton's laws of motion. So every time we use driving force minus resistive force equals to mass into acceleration, that is basically Newton's law of motion, okay? So we'll start with simple pulley problems, okay? When two particles are hanging from a pulley vertically, okay? In some cases you will have one particle at a certain angle, in some cases you'll have one particle on a horizontal floor or a horizontal surface, one hanging vertically, but for now we're going to do questions where two particles are hanging vertically only, okay? So today's date 16th of March 2024, okay? Now, a couple of terminologies, although we've gone over them, but since we're starting something in which we'll be dealing with these terms all over again, so might as well go over them one more time. So every time you read string, or every time there's a string involved, you'll notice that the question uses these two words, light and inextensible. Now, what's the reason behind that? What's the reason behind the question using these two words? Light means that the mass is negligible. Okay, that's one reason. Well, I mean that's one because of light. This is what we mean, that the mass is going to be negligible, and the other is that the tension in the string remains the same throughout. Okay, the tension is same. Okay, and you won't ever come across where you have to consider the mass of the string. Okay. Due to the fact that it's inextensible, the acceleration is going to be the same, but as long as it's taut, okay? Acceleration is same as long as the string is taut. And I hope you guys understand what we mean by taut. T-A-U-T, taut, not T-A-U-G-H-T. What do we mean by taut? We discussed this, I think, in the last class, did we? Okay, now I know what you guys meant by low energy levels, but still I'd like you guys to answer my question. What do we mean by taut? Non-elastic, yes, okay, good job. Okay, so pulley is going to be fixed and smooth, okay? Completely stretched, yeah, completely stretched. Okay, so it's inextensible, that means that is the max it can possibly be stretched, okay? And it has tension in it. Taut means that it has tension in it. Like for example, this string, this wire right now, okay, at the moment it's slack, but if I pull it or if I like hang some weight at the bottom, then there's tension, okay? So that's what it means, that it has tension. The pulley is going to be fixed and smooth. Now fixed means that there's no acceleration induced because of the pulley. Like if the pulley starts to move, that means now it's the movement of the pulley that's inducing acceleration as well. But that's not going to be the case, number one. And smooth means there is no friction that you have to deal with. Okay, the pulley is going to be fixed and there is going to be no friction. Okay, and don't think you won't. Don't worry. You won't have some other case to deal with at any point. Okay. Now let's start with a very basic case. Okay. So the diagram will always look like this. You will have a beam. Okay. Beam basically means any surface where the pulley is hanged, okay, or where the pulley is fixed. All right. And a pulley is always circular in shape. So here's your pulley. Okay, it's hanging from the surface. All right. And then from this pulley, you have two objects or two particles hanging. All right, something like this. And let's say this is A and this is B. Okay, and you can see they're at equal height. All right, and in this case we are going to consider that both of them have the same mass as well. Okay, so let's call this A, let's call this B. Okay, so let's say the mass of particle A is equals to ma, so consequently the weight of A will be equal to ma multiplied by g. W equals to mg, nothing new so far. The mass of B is equal to mb, so consequently the weight of particle B is going to be mb times g. Again, nothing new so far. Tension is represented by the letter T. Okay, now in this case, in this particular example, let's say that the mass of A is equal to the mass of B. All right, so just use your intuition and tell me, what do you expect? What do you expect to happen if both of them are hanging at the same height above the ground, number one, and they both have an equal mass? What will happen? What do you think?
Sir, the Pulley will balance.
Nothing will happen. Sorry, okay, can you repeat what you said? How does it?
Sir, it will balance.
Yeah, it will remain as it
Nothing will-
is. Okay, it will remain as it is. So if MA equals to MB, we say that the system is in equilibrium. Okay, now what's a system? Let's write that down as well. Let's define a system because we're going to be using this term a lot. So a system is basically connected particles with one single string. And because string is singular, that means they have the same acceleration. Connected particles with one single string and acceleration, and once again, as long as the string is taut. Okay, now I've used this 2 times now, as long as the string is taut. Now why do you think I'm putting so much emphasis on it? Why do you think I'm putting so much emphasis on the fact that it will have the same acceleration as long as the string is taut? What happens when the string is not taut? Think about it. Tension becomes 0. Yes, tension becomes 0. And not only the fact that tension becomes 0, yes, but now then the particle will be under free fall conditions. Okay, now if that makes sense to you, perfectly all right. If it doesn't make sense to you, don't worry about it. I have something to help you visualize that. Okay, so here's case number 2. Now in most of the questions that we have, you won't ever deal with a case where the two have equal mass. Okay, this was just to give you an idea that what happens if the mass are equal. Usually you will find that mass of one object is greater than the mass of the other. Okay, so in this case we're going to say that let the mass of object A be greater than the mass of object B. Okay, then as a result, what happens? Due to the difference in weight, because if the mass is different, obviously the weight is different. Due to the difference in weight, the system will accelerate. Okay, the difference in weight will cause acceleration. So let's write that down. The difference in weight will cause or will result in acceleration. Okay, but the question is where will it move? As in, which particle moves where? Does A move down, B move up? If A moves down, B obviously will move up. Both of them can't move down at the same time. Or is B going to move down and A going to move up? A moves down. Reason is the heavier particle always moves down. Okay, so I'll make a note of this. Object, this is something that we always do. Okay, it's always the object with greater mass that moves down. So object with greater mass moves down. Always. Okay, so before we decide let's say before we take the movement into consideration, let's write down all the forces that are acting. Sir, was the acceleration 0 in the first case? Yeah, acceleration in the first case is 0 because not because it's moving at a constant velocity, because it's not moving at all. Okay, in the first case they're not going to move at all. Okay, which means the acceleration is 0. So let's first have a look at all the forces that are acting. So the weight of A will be acting downwards, all right, and what would be the weight equal to? The weight of A will be equal to ma times g. The weight of B will also be acting downwards. Okay, remember, irrespective of the direction in which the object is moving, weight always acts downwards, all right. So WB is equals to mb times g. G is acceleration due to gravity. Okay, tension, as we know, always moves away from the particle. Okay, tension always acts away from the object or the particle. Okay, now because A has a greater mass, that means A will move downwards, A will accelerate downwards, and consequently B will accelerate upwards. Okay, why? Because there's a string which is passing through the pulley, so if A moves down, B moves up. Okay, now let's talk about let's apply Newton's second law of motion on particle A. So what's the force that's acting downwards? Which force is the greater force? The downward force. Why? Because it's moving down. So definitely the downward force is greater than the upward force. So the downward force, which is basically ma times g, minus the upward force, which is tension, is equal to mass into acceleration. All right, this is the net force, which is equal to mass of A into acceleration. All right, so this is for particle A. For particle B, let's have a look at what's going to happen at particle B. Particle B will move up. Okay, it will accelerate upwards. That means it's the upward force that will be considered the greater force, which is tension, minus the mass of B times g minus the downward force. Okay, the force that's trying to stop it from moving up is equal to mass into acceleration. Okay, now this is your first equation, this is your second equation. What happens if I add the two equations? First, in fact, before you answer that question, tell me if you understand what I've done. Or tell me if you have any questions so far.
Sir, could you explain this part once again?
Yeah, sure I can. Okay. So basically what we're trying to do is we're trying to find out the resultant force. Yes, T cancels out when we add them. So since A is moving down, okay, that means the force that's pulling it down, which is its weight, is the greater force. Okay, so the driving force or the downward force minus the upward force equals to the net force, which is equal to mass into acceleration. So that's what we have done. The downward force, the force that's trying to make A move down, minus the force that's trying to stop it from moving down, equals to mass into acceleration, which is the net force. As far as B is concerned, since B is moving up, that's got to mean that the force acting upwards is the greater force. So the force that's acting upwards minus the force that's acting in the opposite direction, that is the force that's acting downwards, is equal to the net force, which is once again mass into acceleration. Okay, that's what I've done. All right, now,
Okay, right.
if I add the two, notice that we have mag minus mbg. So mass of A times g minus mass of B times g, and then minus T plus T, so tension cancels out. Okay, tension is eliminated, is equal to m A into A plus mb into A. Okay, now notice what I said earlier, that the difference in weight will cause acceleration. Now what's mag minus mbg? This is technically the difference in weight, and what's happening over here? This is causing acceleration. So exactly what we said earlier is what we see happening through once we resolve the forces. So this is equal to, if you want, you can take A common, which is equal to ma plus mp. And now you can see that here you have the difference in the weights, which results in acceleration. Okay, and these are the two equations that we will form every single time, and these are the two equations we will use in order to find what? In order to find tension and acceleration. Okay, it's very simple. Just do it particle by particle. First resolve all the forces acting on one particle, then move on to the other, add the two equations, tension will cancel out, and that's it, job done. Okay, so we'll do an example question. You'll notice that you have exactly questions. This is not like a very basic level, but you have exactly questions like these in past papers as well. Okay, now, so let's have a look at an example question from past papers to give you guys an idea of what I mean. Anyway, so this is an example question. It's this is a past paper question. Sorry, February March 2018, paper 4, variant 2. Okay, now in some cases, like for example in this question here, you can see the diagram is already drawn. Brilliant. If not, then just draw it yourself. Okay, and this is what we call a free body diagram. Now, so here we have a pulley, and you don't really have to draw a horizontal, I mean, you don't really have to show that the pulley is fixed on a horizontal surface or any surface. Just start from the pulley. Okay, so here you have a pulley. Let's read the question first. Two particles A and B of masses 0.8 and 0.2 kg are connected by a light and extensible string passes over a fixed smooth pulley. So again, light and extensible, fixed and smooth. The particles hang vertically. The system is released from rest. Show that the acceleration of A has magnitude 6 meter per second square and find the tension in the string. Now, don't be confused. It's not that only A will have acceleration of 6 meter per second square. B will also have the same acceleration. Reason is because they're connected. It's because they're joined. All right, like what we saw earlier, when two particles are connected, and if one particle accelerates at a certain has a certain acceleration, the other particle also will have the exact same acceleration. It's like the train example that I gave, the train and the carriages. Okay, so here we have two particles. Okay, let's consider this as A, let's consider this as B. Okay, now A has a mass of 0.8. Okay, so instead of writing A here, I'll write 0.8 kg here, and I'll write A over here. Instead of writing B here, I'll write B here, and inside I'll write 0.2 kg. Okay, so what would be the weight of A? What would be the force acting downwards? The force that's acting downwards would be 8 Newton. The force that's acting upwards would be T. Okay, we don't know what that force is. All right, so as far as A is concerned, since A is the heavier particle, we know that A will move downwards, and consequently B will end up moving upwards. All right, so if you talk about A, that's going to be 8 Newton minus the upward force, which is T, is equals to 0.8. This is our first equation. Let's talk about B. Now B, since it's moving up, that means the tension is the greater force, and the force that's acting downwards, the 2 Newton force, is the lesser force. So T minus 2 is equal to what? Is equal to 0.2A. All right, what happens if I add the two? Tension cancels out. 8 minus 2 is 6. 6 is equals to 1A, and there you go. A is equal to 6 meter per second square. Right, and how many marks do you get for this? You get 4 marks. In fact, not 4 marks. Yeah, okay, you have to find the tension as well. Okay, so still a pretty good deal. Okay, now we've shown that the acceleration is 6 meter per second square. Now, how will I find the value of tension? Or how will I find out the tension in the string? Question for you guys. See if you can answer it. I'm sure you can. What should I do? Substitute. That's correct. Substitute the value of A in any one of the two equations. So let's go with 8 minus T is equals to 0.8 into A. So 8 minus T is equals to 4.8. If I'm not wrong, 8 6 are 48. Okay, it's best to choose calculator. 8 into 0.6 is 4.8. 8 minus the answer is 16 upon 5. So T is equals to 3.2 Newton. And that's it. Job done. 4 easy marks. And look at the amount of space that you're given. So, any questions? If yes, feel free to ask. If not, then I have another question for you guys to solve.
सर इसका आप ओवरव्यू दे सकते हैं आगे?
Sure. So, देखो, you have a pulley, and from the pulley you have two particles that are hanging vertically. Okay. One particle is heavier than the other, which is what results in acceleration. Okay, if they both had the same mass as we saw in the first case, that would have meant that it's in equilibrium. Okay. Now, the idea is that the heavier particle always comes down. All right. If you use your logic, also it makes sense. The heavier particle will always come down because of the fact that it's heavier, the downward force is greater. Okay. Now, what's the force with which it's going to come down? The force with which it's going to come down is the weight. Okay, nobody's pushing it down. It's its own weight that's bringing it down. Now there's got to be some force acting in the opposite direction as well, and that's tension. Okay, tension, as we know, always moves away from the object. So 8 minus t, the downward force minus the upward force, is equal to the mass into acceleration, Newton's second law of motion. Now we talk about B. Since B is moving up, that means the upward force is the greater force. So the upward force minus the downward force, which is its weight, remember, will always act downwards, is equal to its mass into its acceleration. Okay, and the acceleration will be the same throughout. Why? Because they're connected. Now, technically what we have done is, with the information given, we've formed two equations so that we can solve them simultaneously. And the reason behind forming two equations is because we have two unknowns. One is the tension, the other is the acceleration. Okay, so with the help of one particle, we form one equation. With the help of the other particle, we form the other equation. Then you solve them simultaneously, which means you add the two. I mean, you can use elimination, you can use substitution, but elimination is something that will always work. So it would be silly to use substitution over here. Okay, so you add the two. As a result, tension cancels out, which gives you the value of A. And once you have the value of A, you can use any one of the two equations to find out the value of T. That's it. Job done. Okay?
Right, yes, thank you.
You're welcome. Alright, now here's a question which I'd like you guys to solve. There is a part 2 of this question, but I don't want you guys to do part 2 because we are going to first do Pulley and kinematics. That is when things get really interesting, when it comes under free fall. So we'll do that first and then we'll do the remaining parts, but first I want you to solve this. Okay, looks like we have an answer. A is 10 upon 3, that is correct. It's given. And T is 2.67. Okay, I'll just wait for a minute for the rest of you to complete the question and then we'll move on. Okay, correct. T is equal to 8 upon 3. Anyone who's not getting the correct answer, please let me know. Although I really hope that's not the case because it's a very easy question. All of you should be able to solve it. Okay, I'll just quickly make the two equations so you can see where you're going wrong if you've gone wrong. 4 minus T is equals to 0.4A for particle A. Then T minus 2 equals to 0.2A. Add the two equations, find out the value of A. Should be 10 upon 3. If it's not, you're doing something wrong. And then find out the tension in the string. So T, if you do it correctly, should be 8 upon 3 Newton. Okay. All right. Now, the next concept that we're going to do is Pulley and kinematics. Okay, this is where, like I said, things get really interesting. Now in fact, let me write this down. Then I want you guys to watch a video, make a mental note of it. Okay, and then we'll watch the video again. Okay, so I'm not going to ask you any follow-up questions after you guys watch this video, but I just want you to watch this video very carefully. Okay, and just make whatever mental notes you can. All right, so here it is. There you go. You have two systems. You have two particles in at rest initially, and as soon as the system is released from rest, notice what happens. One hits the ground and then this goes further up. Okay, so once again, watch it, make some mental notes, and then we'll discuss what exactly is going on. Okay, so I'll show you guys in slow motion as well if you want. So here we go. By the way, this is a video that I've taken. I don't own this video, I should mention. Okay, great. So now coming back, Pulley and kinematics. Now where does kinematics, or how does kinematics fit in here? Okay, how come we all of a sudden have kinematics to deal with? Let's see. So we'll start with an example. We'll start with a situation right here. Okay, so here you have a pulley. Okay, and from this pulley you have two objects hanging, A and B. A is the heavier one. Okay, and A is 1 meter above the ground and B is 1 meter further above from A. Okay, so this is particle B. All right, so once again, You have a pulley, and from the pulley you have two particles hanging. A is 1 meter above the ground and B is 1 meter further above A. Okay, now what will happen as soon as we release this system? What will happen as soon as the system is released? Question for you guys.
A will go further down, sir.
A will go down, and if A goes down, what happens to B? B goes up. Okay, so as soon as we release the system from equilibrium, here's what happens. A falls down. Okay, so here we have A, which falls down, touches the ground. Okay, and if A falls 1 meter, A falls 1 meter to the ground, then what happens to B? B
will rise 1 meter.
B will rise 1 meter. All right, that's correct. So consequently, B rises 1 meter. Okay. Achha. But that's not the only thing that's going to happen. So this is not drawn to scale, but this distance is also 1 meter. Okay. And how far above now will B be from the ground? Although not asked, but just so you know, B will now be 3 meters above the ground. Okay, initially it was 2 meters, but now since A has fallen down 1 meter, which means B has gone up 1 meter, so now it's a total of 3 meters above the ground. Okay, so this is what happens as soon as A hits the ground. Okay, so I'll make a note over here. A falls 1 meter, B rises 1 meter. So A falls 1 meter and consequently B rises 1 meter. Okay, any confusions? If yes, feel free to ask. Okay.
Basically, the A fall करेगा उतना ही B rise करेगा.
Yeah, obviously, because they're connected. So, जितना A fall करेगा उतना ही B rise करेगा. Correct. Okay, then as soon as A hits the ground, the string becomes slack momentarily. Okay, as soon as A hits the ground, the string becomes slack. And what will happen to B as a result? See, A can't go further down. Okay, A has hit the ground, it can't go further down. But what will happen to B? Think about it. Try and recall the video that you just saw. What happens to B? B goes, B rises further. Okay, so what happens as soon as A hits the ground? Okay, the string becomes slack, and B, because of its momentum, because of the momentum that it gained while it was going up, it rises further. Okay, now what happens to A's momentum? Because it hits the ground, the velocity instantly becomes 0. But B still has some momentum to lose. Okay, and it's due to that momentum B rises further. Okay, so initially this is where B was. Okay, this is where B was. But now, because of its momentum and because of the fact that the string is now slack, B moves further up. Okay, so now the string is slack, and because of that, B moves further up. And for this distance, just a minute. For this distance, this very small amount of distance that B moves up, it's under free fall. Okay, why? Because there's no, it is connected, it's still connected with the string, but it's slack, which means there's no tension. And if there's no tension, what is it that's moving, that's causing it to move up? It's its own momentum, and it is now under free fall. Okay, so for this fraction of the distance, very small amount of distance, and for a very small amount of time, B is under free fall conditions. Okay, I'll explain this again. Now, instead of explaining this again, here's what I'll make you guys do. I'll make you rewatch the video. Okay, so let's watch this video again, and now it will make more sense. I'll zoom out so you can see everything that I've drawn over here, and let's watch this video.
Travel.
So here's A and here's B. Okay, now notice what happens as soon as the system is released from equilibrium, and this is the ground, by the way. A hits the ground, and as soon as A hits the ground, now over here we can see that A bounces up. Okay, but for a minute, let's ignore the fact that A is going to bounce up. But as soon as A hits the ground, notice what happens to B. B rises further up, okay, and then comes back down. So once again, have a look. System is released, A hits the ground, B rises further up, it's under free fall, and then it comes back down. Okay, so let's apply that over here. The system is at rest, A is released, okay, A hits the ground, B rises 1 meter up, okay, B rises 1 meter from the point it was at initially. Then the string becomes slack. When the string becomes slack, because B still has a bit of momentum, B further rises up, okay, and during this time it's under free fall conditions, okay. And if it's under free fall, what will be its acceleration, by the way? If it's under free fall and it's going up, what will be its acceleration? Not 10, minus 10 actually. If it's going up, it's minus 10. And then on the way back down, it will be positive 10. Okay, on the way back down, up until the point that the string becomes taut again, it will be positive 10. Okay, understood? I'm going to write down a couple of key points, but still, if you have any, while I'm doing that, if you have any questions, feel free to ask. So, first of all, the final velocity of A, let's call it VA, in the sense that just before it hits the ground, not after it hits the ground, because we know after it hits the ground it's going to be 0, but the final velocity just before it hits the ground, which is VA. Now what do you think this velocity will be equal to compared to B? What will be this velocity compared to B? Or what will be this velocity of B? The final velocity of A will be what velocity of B? The same, that's correct. Same, but it's going to be the initial velocity. Okay, the final velocity of A, which is VA, is now the initial velocity of B. Is now the initial velocity of B, which means it is now UB. Okay, why? I'll explain. Once again, have a look here. So notice the velocity with which A hits the ground. Okay, now first of all, understand that they're both moving at the same velocity. Okay, now the velocity with which A hits the ground, that's the velocity with which B rises. Okay, that is the initial velocity of B just from that point onwards when it's in free fall. Okay, so here, have a look. The velocity with which A hits the ground is the velocity of B, but it's the initial velocity. Okay, the final velocity of A is equal to the initial velocity of B. Understood? You guys understand? Don't memorize this, but tell me, make sure that you understand the reason why. Because they're both connected. They're both connected by a string. So the initial velocity of A, the speed with which A hits the ground, is the speed with which B rises when the string becomes slack. Clear? Clear to everyone? Okay. Now what can you tell me about the final velocity of B? Final velocity of B. Sir, why are they moving with same velocity? Yeah, because they're connected. Because they're connected. It's like, once again, go back to the train and carriage example. If you have a train and if the engine of the train starts moving, what happens to all the carriages that are behind? They also move at the same velocity. Why? Because they're connected. Because they're connected. It's practically not possible for two of them. Same acceleration also for the same reason. It's not possible for two of them to experience different acceleration. It's like, I'll give you another example, a very basic example. When you're sitting on a plane, okay, technically you're also moving, right? If you're sitting on a plane, or let's not talk about a plane, let's talk about a car. Let's talk about a car. If you're sitting in a car and you're traveling, if the car is accelerating, what's happening to you at the same time? You're also accelerating. Okay? Relative to the car, yes, you're not, but वैसे तो you're accelerating, right? Why? Because although you're not connected, but you're in the same system. You're still part of the same system. Okay, so just like that, here, because they're connected, they for that reason they have the same acceleration, and for that reason they have the same velocity as well. Okay, clear? Sir, why can't we say initial velocity of A equals to initial velocity of B. Okay, so here's what we're doing. So A's journey ends, okay, A's journey ends as soon as it hits the ground, all right? That's the end of A's journey, which is why it's final velocity. For B, the velocity that we're considering, the part of the journey that we're considering is the part where it's under free fall. Okay, so just when it starts to be under free fall conditions, that is what we're considering, which is why we're saying the initial velocity of B. Okay, so that's the part of the journey of B that we're considering. Not the journey throughout, just the part where it's under free fall. Okay, I'll repeat what I said. So for A's journey ends as soon as it hits the ground. For B, the part of the journey of B that we're interested in is the part where it's under free fall. Okay, so here you can see this is the point where B's free fall starts. Okay, this is the point where B's free fall starts. Now the speed at which A hits the ground, the final velocity of A, is going to be the speed with which B starts to rise further. Okay, that's going to be its initial velocity. And remember, once again, for B, the part of the journey that we're considering is the part where it's under free fall. Okay, then when B reaches its maximum height, okay, it's going to rise a bit further up and then it's going to come back down. So when it reaches its maximum height, although I already asked this question, you guys have already answered it, but what would be its velocity? What would be the final velocity of B? 0. That's correct. The final velocity of B, which is VB, equals to 0. Okay, so this is something that we have done earlier as well. When you throw an object up, as soon as it reaches its maximum height, the velocity is 0. In fact, the reason why it's reached its maximum height is because velocity is 0. If the velocity wasn't 0, it would still be moving up. Okay? Now, another rule of kinematics, and that is T1, which is basically the time it takes to go up and the time it takes to come back down, up until the point that the string becomes taut again, will be what? Will be equal. Okay, so T1, basically the point from where the string is slack and the particle is moving up, okay, is equal to T2. And what's T2? T2 is when the string is slack but the particle is on the way down. So when does the string become taut again? When B comes back down. When B comes back down, that's when the string becomes taut again. Here, have a look. So it's A hits the ground, B rises further up, reaches its maximum height, and then when it comes back down, the string is taut again. That's when its acceleration will not be equal to 10. What do you mean? When will the acceleration not be equal to 10? I'm not sure I understand. When the string becomes taut? Okay, when the string becomes taut, then that's the point where it stops moving. Okay, and that is when the acceleration is 0 because it comes to rest. When the string becomes taut and it comes to its initial, it reaches this position, again, that is when the acceleration is 0. Why? Because it's at rest. Okay. All right. Then the final velocity on the way down. Okay. I know it's getting confusing, but this is the last point. The final velocity of B on the way down, just before the point where it comes to rest or when the string becomes taut, will be equal to what? The final velocity on the way down will be equal to the initial velocity on the way up. Okay, so key point number 1. On the way down, just before the point where the string becomes taut. Why? Because the second the string becomes taut, it comes to rest. But on the way down, the final velocity of B, we're talking about on the way down, okay? The final velocity of B is equal to the initial velocity of B, okay? Just like something that we learned in kinematics. If you throw an object up in the air, on the way down, when it reaches the same point from where it was thrown or projected, the velocity is equal to the velocity at which it was thrown. Okay, so I repeat, if you can you remember all these details? Okay, you don't have to remember all these details. These details aren't relative to Pulley. These details are basically the same as the ones we did in kinematics, especially these details. They're basically the standard rules of kinematics, which is why this is called Pulleyan kinematics. Okay, I'll repeat. Dekho. Remember we did questions when a particle was projected up in the air, right? A particle was thrown up in the air or it was projected up in the air with a certain velocity. Okay, now when that particle comes back down and it reaches the point from where it was projected, okay, so let's say here is the point of projection, which is a certain distance above the ground, okay, and let's say it's projected at 12 meters per second. Okay, so we know what the trajectory is going to be. The trajectory is going to be that it's going to go up, it's going to reach its maximum height. Okay, now all this is going to happen vertically, but we draw it we draw it in curve form so that we can see the whole trajectory. Okay, so it's going to go up, reach its maximum height, come back down. Now when it reaches the point of projection, the speed will be the same at which it was thrown up, correct? And the time it takes to reach its maximum height, let's say it takes 10 seconds. Okay, let's say it takes 10 seconds to reach its maximum height. Okay, so on the way up, let's say that it takes 10 seconds. So if it takes 10 seconds to go up and reach its maximum height, how long will it take to come back down? T equals 10 seconds. Okay, so these rules, like I said, these are kinematics rules. Okay, they're not applied, they're not just being applied to Pulley related problems. They are rules that we apply in kinematics anyway. Okay, now the questions aren't that complicated. All right, I'll solve a question, you guys will understand what I'm saying. They're not that complicated, but you got to remember these rules. Okay, no two ways about it, you got to remember these rules. Now let's solve a question to understand what it's like. Okay, the first part I'd like you guys to solve without my help. A is 2.5, that's correct, good job Abdullah. H is 0.45, that's correct. So 6 easy marks, don't you think? A is 2.5 meter per second square, or 5 upon 2, okay. How? Here's how. 5 minus t equals to 0.5a, the first equation. T minus 3 equals to 0.3a, the second equation. Add the two. 2 is equals to 0.8a, which means a is equals to 20 upon 8, which is 5 upon 2. Yeah, 2.5 meter per second square. Okay. Then the next part where we have to find out the value of h, what do we do? What do we do to find out the value of h, fellas? Yeah, we use Suvat equation. So particularly this equation, s equals to ut plus half at square. Okay, so s is equals to ut. So since initially it was at rest, okay, I hope you guys have all read the question. So this becomes 0 plus 1 upon 2 into a, which is 2.5, into, we're given the time that it takes to reach the floor, or reach the ground floor actually, which is 0.6, and then you work this out, so h equals to 0.45 meter. Okay, now you can see gradually how kinematics is showing up in pulley problems. Okay, now this is not it, this is the first part. Here's the second part. Q remains at rest when it reaches the floor. P continues to move upwards, just like what we saw earlier. When A hits the ground, it comes to rest, but B still had some momentum, which is why it kept moving upwards. Find the velocity of P at the instant when Q reaches the floor and the total time from the instant at which Q is released until the string becomes taut again. Okay, so take some time to understand what the question is saying. Find the time at which, find the velocity of P at the instant when Q reaches the floor. Just a minute. I'll copy paste this diagram here so that it's easy for you. To visualize the whole situation. Yeah, here we go. Okay, so find the velocity of P at the instant when Q reaches the floor and the total time taken for the instant at which Q is released until the string becomes taut again. Okay, first we find final velocity of Q, then we use, yeah, that's correct. So in order to find out the velocity of P at the instant when Q reaches the floor, for that you can also find out the final velocity of Q when it reaches the ground. Okay, because they're connected, both the velocity will be the same. Okay, V of Q. Okay, so I'll give you guys how many marks is this? 3 marks. Okay, I'll give you guys 3 minutes to figure it out. Okay, and after that I will solve the question for you guys, but I really want you guys to try it yourself. Okay, so a good idea would be to visualize the whole situation and break down the journey of P. Okay, so the journey of P can be divided into 3 parts. All right, what are those 3 parts? The first part is when it reaches the ground. Sorry, P doesn't reach the ground. Sorry, the first part is when Q reaches the ground and P rises h meter, which is basically 0.45 meters. Okay, that's the first part of P's journey. Then the second part is when it further rises. Okay, the second part is when it further, the string becomes slack and then it further rises up. That's the second part of the journey. So here's the first part. The second part is when it's going up, and the third part is when it's coming back down up until the point that the string becomes slack again. Okay, so I repeat the 3 parts of P's journey. The first part is when P goes up as a result of Q falling down. Then the second part is also when it's moving up, but now it's moving under free fall. Okay, now it's under free fall conditions. Then the third part is when it's coming back down, still under free fall, but it's going to come back down, or it's going to remain under free fall until the string becomes taut again. Okay, I hope that part is clear. Okay, the question says find the velocity of P at the instant when Q reaches the floor and the total time taken from the instant at which Q is released until the string becomes taut again. Okay, so first let's focus on the first part of the question, which says find the velocity of P at the instant when Q reaches the floor. So whether we find out the final velocity of Q or whether I find out the velocity of P, it's the same thing. Why? Because V is equals to U plus AT is what we're going to use. The initial velocity of both of them is 0. Okay, the final velocity of P can be simply worked out by doing 0 plus A. Now acceleration will be the same of both because they're connected, 2.5, and we know that the point where it in the first part of the journey, the first part of the journey consists is just 0.6 seconds long, so we can find out the velocity at which it reaches in 0.6 seconds. Okay, so V is equals to 2.5 into 0.6. Let's see what that is. That is 1.5, which most of you got correct. In fact, nearly all of you got this correct. Okay, so this is the first part of the journey, and remember we're talking about particle P. Okay, we're talking about particle P, and this is the first part. Then comes the second part. Now it's under free fall. Okay, in the second part of the journey it's under free fall. Now what would be the initial velocity when it's under free fall? Question for you guys. Now free fall starts. What would be the initial velocity when it's under free fall? 1.5, that's correct. Okay, the initial velocity when it's under free fall would be 1.5 meters per second. How 1.5? Okay, देखो. P travels up, okay, the first part of the journey. The final velocity of the first part of the journey then becomes the initial velocity of the second part of the journey. Okay, so the first part of the journey is when the string is taut. Okay, P travels up. P travels up, the string becomes slack. Now what's the speed at which it's going to continue to move up? That would be this ending speed or the final speed of the first part of the journey. Do you understand? P moves up, okay, and then the first part of the journey ends. That means there's no more tension in the string, but P continues to move up. Why? Because of the momentum, okay, because of the velocity that it has. And what's that velocity? That velocity is 1.5. And where did 1.5 come from? 1.5 is the final velocity of P while it was moving up when the string was taut. Make sense? Okay. The same thing as we saw earlier. Okay, but here, since we have to consider P's journey of the part where the string is taut, earlier the question that we looked at, the example that we looked at, we said that the velocity at which Q hits the ground becomes the initial velocity at which P will start to rise under free fall. So here also we're doing the same thing. This velocity, by the way, we're saying that it's the velocity of P, but it won't just be the velocity of P, it will be the velocity of Q also, at which it hits the ground. And then this velocity will now be the initial velocity of P with which it moves up. Okay? Now when it reaches its maximum height, here, when it reaches its maximum height, what would be its velocity? That's correct. V equals to 0. What would be the acceleration? Remember, it's going up. Okay, it's going up. Minus 10. Good job. What's the time? We don't know, but we can work it out using the same equation. V equals to U plus 80. So V is 0, U is 1.5, minus 10t. So t is equals to 0.15 seconds. Now going back to the third or fourth key point that we wrote, this is the velocity, this is the time that it takes to go up. How long will it take to come back down? For the third part of the journey, when it's coming back down, it will take the same amount of time, 0.15. Now let's go back to the question. The question asked us to find out the total time from the instant at which Q is released until the string becomes taut again. So that means we need to find out the total time of the three journeys. So the first part of the journey was 0.6 seconds. The second part of the journey, 0.15. The third part of the journey, also 0.15. So altogether, 0.9 seconds. There you go. Now take a good look at it. Let me know if you have any questions. Overview? Yeah, of course I can do that. Not a problem. Okay. So here's what happens. Q is now released. I'm reading from this point onwards. Q is now released and both particles start to move. Now, as soon as Q is released, what happens is that Q moves down because it's heavier, P moves up. Okay. Now, Q hits the ground and Q falls h meters, which we worked out to be 0.45, and as a result, P rises 0.45 meters up until the point the string, and up until this point the string was taut. Okay. But the second that Q hits the ground, the string becomes slack. Okay, and P, because it has some velocity, it was still going up. Because of that velocity, because of that momentum, it will continue to move up. Okay, and here we've illustrated just that. Q hits the ground, P, the amount of distance that Q falls, P rises that distance, and then P, now under free fall, rises a further distance and then comes back down. Okay, now the velocity with which Q hits the ground is the velocity with which P travels 0.45 meters, okay, or is the velocity that P reaches in 0.6 seconds. And up until 0.6 seconds, the string was taut. Now, after 0.6 seconds, the string becomes slack for a certain period of time, okay. Now, what is the time that it takes to reach its maximum height? Now, before we talk about its maximum height, let's talk about the velocity. The initial velocity, now we're talking about the second part of the journey. So when I say initial velocity, I mean the initial velocity of the second part of the journey. So in the second part of the journey, the initial velocity is 1.5. Okay. Now, if the initial velocity is 1.5, what would be the final velocity? 0. And why is the initial velocity 1.5? Because as soon as the first part of the journey ended, its final velocity was 1.5. Now the second part of the journey, initial velocity is 1.5. Okay. So initial velocity 1.5, final velocity 0. We find out the time that it takes to reach its maximum height, 1.5. So the amount of time that it takes to go up, it will take the same amount of time to come back down up until the point that the string becomes taut again, and that would also be 0.15. So 0.6 plus 0.15 plus 0.15 is 0.9 seconds, which is the total time taken from the instant at which Q was released until the string becomes taut again. Yes, 0.6 seconds was obviously given in the question. It's right here. 0.6 seconds. Okay, now remember the first question that we did where I only made you guys solve the first part? So we're going to go back to that question. Just a minute. Okay, so this question that I made you guys solve, you showed that the acceleration is indeed 10 upon 3 and tension is 8 upon 3. Now this question has a follow-up part. It says when the 0.8 kg particle reaches the floor, it comes to rest. Find the greatest height of the 0.2 kg particle above the floor. Okay, so it's just a continuation of the previous question, and this is the last question of today. I'll write down the value of t, although the value of t here is irrelevant, but I'll write it down anyway. 8 upon 3 Newton, and the acceleration 10 upon 3 meter per second square. Okay, so 3 easy marks. Solve this, and that's it. We're done for the day. Okay, I'll solve this question. All right, so the 0.8 kg particle hits the ground. Here it is. And the 0.2 kg particle rises 0.5 meters up. Okay, now it was already 0.5 meters above the ground. Now it rises another 0.5. Okay, so that means whatever the height is, it's going to be more than 1. Okay, then the string becomes slack. Okay, and then as soon as the string becomes slack, the 0.2 kg particle rises further up. Okay, and then if it's going back up, it's going to come back down also. Okay, now before I can find out the greatest height, what I need to do is I need to find out the final velocity of the first part of the journey when the string was taut. So the final velocity of the first part of the journey when the string was taut can be worked out by, first let's write down the information. So we have the acceleration, we have the distance 0.5. okay, and just so you know, the first part of the journey is when the 0.2 kg particle is moving up and the string is taut, which is why what is the acceleration that we're taking? We're taking 6 meter per second square. The initial velocity is 0, and we need to find out the final velocity. So you can see what this is pointing towards is this equation only. 2as equals to v square minus u square. So 2 into 6 into 0.5 equals to simply v square. So v becomes what? V becomes, let's see, 2 into 6 is 12, 12 into 0.5 then becomes under root 6. V is under root 6, is that correct? Yeah, V is under root 6. Okay. Now, to find out the greatest height, then when the 0.2 kg particle is again moving up, but this time it's moving under free fall. Okay, this time it's moving under free fall. That is when the initial velocity will be root 6 and the final velocity will be 0 when it reaches its maximum height. The distance we have to find out, the acceleration due to gravity will be minus 10. Okay, so once again we use the same equation, 2as equals to v square minus u square. So 2 into minus 10 into s equals to v square, which is 0, minus root 6, the whole thing square. Okay, So we have minus 20s, which is equal to minus 6, minus minus cancel, and s is equals to 0.3 meters. Okay, now it reaches 0.3 meters. Basically, it rises another 0.3 meters. So what will be its maximum height? 0.5 meters. It was already above the ground, 0.5 meters. It moved up since one particle came down 0.5 meters, and then an additional 0.3 meters, which means that it's now 1.3 meters above the ground, which is its maximum height. Okay, so you still think it's as difficult as how you thought it was in the beginning? Okay, I'm glad you feel that way. All right, I'll explain the last part again. So in the last part, so basically, again, let's divide the journey into two parts. One part is when it's moving up while the string is taut. So what's the distance that it moves up while the string is taut? 0.5 meters. Because 0.8 kg particle falls down 0.5 meters, the other particle moves 0.5 kg above. Okay. Then it's still moving up, but now it's moving up under free fall. Okay, so the final velocity of the first part of the journey will now be the initial velocity of the second part of the journey. The final velocity will be 0 when it reaches its maximum height. The distance, we don't know. Acceleration will now be due to gravity, and since it's moving up, it's going to be minus 10. So we use this equation to find out the distance, which is 0.3 meters. This 0.3 meters is the distance that it moves further up. Now, what is the total distance or the greatest height of the 0.2 kg particle above the floor? It was already 0.5 meters above the floor, then it moved another 0.5 meters while the string was taut, then it moved another 0.3 meters while the string was slack. So the total distance or the greatest height above the floor would be 0.5 plus 0.5 plus 1, 0.3, which is equal to 1.3. Okay? Make sense?
Yes, sir, makes sense.
Alright, good to hear that. Okay, so we'll keep it till here only. Alright, and I'll give you guys some questions to solve. We have a class tomorrow. Tomorrow, inshallah, we'll do friction and hopefully be able to complete it also. Okay, at least do all the concepts, and maybe for questions, we'll have another class. Okay, so I'll stop here. About P1, I'll let you guys know whether we're having a P1 class tomorrow or not. Love this.